All right. Welcome, everyone. Welcome all remote EPiC people. For those who are remote, this is the EPiC monthly seminar that we plan to have. Sorry if you don't have pizza at your site. And we also have people here at Chicago, in addition to our group, because this is public master's defense, in fact. This is a little bit unusual today that we have a joint presentation for Adam and Yongshan's work, which comes from actually a series of papers that they've been working on. That work has sort of culminated in this paper called Magic State Functional Units, which they will present in a couple of weeks in Japan, also jointly. So this is sort of an extended version of that talk, which also serves as their master's exam, which also serves as our first EPiC monthly talk. Well, we're real excited to have this, so take it away.
All right. Thank you, Fred, for the introduction. As Fred mentioned, this will be the joint presentation of both of us, and we will be talking about a recent paper that we wrote called Magic State Distillation Function Unit, and specifically we will be talking about mapping and scheduling techniques that we designed for multi-level distillation circuits on fault-tolerant quantum computers. This is a joint project to which both of us contributed equally, and my name is Yongshan. And
I'm Adam Holmes.
So so you can find the paper at this archive reference here. So without further ado, let's get started by looking at by going over the outline of today's talk. So I'll begin by introducing very briefly about quantum error correction, and also a very important component of error correction, magic state distillation, which will be the focus of our talk. And then we'll follow that by introducing our methods and the results that we obtained using those methods for optimizing the distillation circuits. Also, at the end, we will talk about a number of future immediate extension to this line of work. Okay, so to begin with, I'll introduce some very basic concepts in quantum computation. And specifically, a qubit can live in a superposition of two basis states, 0 and 1, and written here at the top of the slide as a linear combination where the two coefficients in front of the two bases are complex numbers that satisfy this normalization criteria, alpha squared plus beta squared equals 1. Alternatively, you can also write this in terms of its spherical coordinates, written at the second line. And it's very convenient because now we can use that spherical coordinates to visualize a qubit, such as this, which is a block sphere diagram. And showing here, the two basis states are actually the two the northern and southern pole of these two of the sphere, and a quantum pure state lives on the surface of the sphere. All right, so that's a very basic introduction of qubit state. This will come handy in our talk later. And just to do a very quick introduction on quantum gates also, I list a number of examples here. The first one is called the X gate, or in other words, the NOT gate, which flips the basis 0 state to 1 state. And visualized on a block sphere, you can see it's a rotation along the x-axis pointing out of the screen by 180 degrees. So the green vector on the left-hand side that points to 0 state will be rotated down to pointing at 1 state. All right, very straightforward. That's the X gate. Next one, another very straightforward one. That's the Z gate. which is similarly a rotation along the z-axis by 180 degrees. So a vector like that on the left-hand side pointing to the positive direction of the x-axis will be rotated to the negative direction of the x-axis. And since these two states are really common in quantum computation, we actually give them a name called the, well, commonly known as Laplace state, which is written as 1 over root 2, 0 plus 1 over root 2, 1. And the negative vector is basically the minus state with the minus sign. Okay? So that's two of the very simple quantum gates. Now, one important property of qubits is that they are very fragile. They suffer from noise, and they can decohere really quickly. So one way to combat that is by doing error correction. And what we will specifically talk about today is one scheme to do error correction called the surface code. And the way to do it is by arranging multiple physical qubits on a surface, and then do some tricks that to allow them to interact with each other so that we have higher fidelity operations on this surface. And to be more precise, what we will introduce is one extra qubit we call ancilla, as you can see on the left-hand side of the circuit, for each of the 4 data qubits, denoted as a gray dot on the screen. And what the ancilla will do is that it will interact with its 4 nearest neighbors, through a series of CNOT gate, which perform the parity check to its neighbors. And there are 2 advantages of this circuit, which we also call it the stabilizer circuit. And this particular one is called the X stabilizer circuit. The first advantage of this circuit is that it can you can measure the ancilla, and the measurement outcome will help you detect a phase flip to any of the data qubit that you are interacting with. All right, and so the second advantage of this circuit is that it also magically forces all of its neighbors to be projected onto a joint eigenstate of the stabilizer. And basically what it does is to force all the data qubits to be in certain pattern of the states. And to be, I guess, complete, we also want to detect bit flip. As I mentioned, X stabilizer detects a phase flip. In order to detect a bit flip, we use a Z-style stabilizer that interleaves with the X stabilizer, as shown on the surface right here. And it's a similar interaction with its 4 nearest neighbors. And what it does is also a measurement on the ancilla in the middle, and it can detect the bit flip of any of the neighbors, and also forces the data qubit to be in a certain state. Okay, so that's the abstraction that we will need for today's purpose. And just to very briefly talk about how the detection makes sense that I mentioned makes sense. So imagine you have a grid of qubits denoted here as circles, and you have, let's say, Z stabilizers between the each 4, I guess, face of the diagram here, and assume you start with the measurement outcome being +1 overall for every single stabilizers. Now, if you found out that there are 2 of these stabilizers showing up as -1 at some point, the one possible error that occurred to this circuit that causes this -1 is, one possibility is that there was a bit flip on the middle qubit, or now a number that's qubit 8 in the middle, and it will cause both of its neighbors, because the detection both of them will see, oh, it's a change in the data qubit state. So so the measurement outcome will be different. So that's one way to utilize the measurement outcome as a syndrome signal to detect error. Okay, and now let's talk about how is this better than single qubit, and how do we make logical qubits out of those physical qubits? Okay, so by physical qubit, I mean the data gray circles on the surface, and by logical qubit, I mean that we introduce extra degree of freedom to the system. And what I mean by that is that if the number of degree of freedom in a system is equal to 2 times the number of qubits on the surface. And however, if you introduce one patch of stabilizer, it removes 2 degrees of freedom. So if you count on the left-hand side, there are about 41 number of data qubits in that square. There are a total of 40 stabilizers. So that leaves us 2 extra degrees of freedom. And what that means is that by doing those syndrome stabilizing circuit, you will project the states. There are multiple states that you won't project them away. For example, if it's 0 degree of freedom, then any operation on the surface will be projected back to one single state. But now you have multiple degrees of freedom. There are multiple states that can be projected to. So now you can imagine some operation that transform from one of the what we call eigenstates to the other as your logical operation on this qubit, on this logical qubit. So that's what we did. For example, to be more, I guess, specific, the X logical operation and Z logical operation are performed by applying physical Z gates to the data qubits along a path denoted as the red line and yellow line on this diagram. So if you do that, it will transform from one of the stabilizer states to the other stabilizer state, and basically that will be denoted as you're transforming the logical qubit state to another. Okay, so that's one way of building a logical qubit. There's multiple ways of doing that, and another way is simply by disable some of the effects, by disable some of the stabilizers to introduce extra degrees of freedom. And this is what we call the double defect qubit. However, you need to be really careful about the geometry, since you can see the line in the middle consists of 3 data qubits, and any noise, like a bit flip happened to, or a phase flip happened to that 3 data qubit will go undetected, and that's error in your surface code scheme. So that's a very basic overview of how what's the role of stabilizers in surface code. Okay, so now you have a bunch of logical qubits, let's say double defect, and we model this, let's say, by a single dot. Right now, the picture shows an array of logical qubits, okay? And each one is basically some structure like this. How do you now interact 2 logical qubits? So the way you do it, one way is by finding a path and do braiding. It has a constraint. 2 braids cannot cross, and it has to wait until other braid was executed. Then you can go and interact with your target. And the reason that it cannot cross is that the underlying mechanism of a braid or a path is basically a pathway of contiguous stabilizers that was disabled along the path. All right, so that corner is basically you took out those Z stabilizers along the way. Now, if you were to cross 2 braids, then you are actually introducing the interaction between the 2 pairs. And that's the general intuition of why braid cannot cross. And that introduces a very unique congestion problem that we want to solve, because if you want to schedule them in parallel, you got to find out which way you route to make it faster, to make it not congested. Okay, so I want to talk about another very important component of the surface code error correction. That's called the magic state distillation. The reason we talk about it is it can be motivated by looking at the gate cost of operations in the surface code error correction. And there are two sets of different gates. One set is cheaper to execute, to implement on surface code. For example, gates from the Clipper group, and the examples I listed here are Hammer gate, S gate, or in other words, space gate, and controlled NOT gate, which require this two qubit interactions involving braiding, for example, are easier to implement compared to another set of gates with an example of T gate shown on the screen. And the T gate is essentially a rotation, if you will look at the blocks here, a rotation about z-axis, along z-axis about 45 degrees. And it's harder to implement. So how hard is that? Let's take a closer look at how to implement T gate. Okay, and so first off, when we say gates are cheap to implement, we typically refer to as that gate being transversal in surface code. And what transversal means that you can just apply your physical gate to each of the data qubits that encodes your logical qubits. Can we do that for T gate? It turns out that if you just apply T gates to all the data qubits, it did not achieve what you wanted. It's not a T logical operation on the logical qubit, nor can you pick any subset of the data to achieve this. So it turns out there are another way of doing this by only applying Clipper gates. In particular, the circuit on the right-hand side is showing what we call the Tpa Injection Circuit, and it involves a set of Clipper gates, in particular a CDOT interaction between two qubits, and a measurement and a post-corrective Clipper correction. That's the phase gate belonging to Clipper gate. However, it requires you have you require that you prepare a special logical qubit state in an event, and we call that the T magic state. Probably keep going.
Just keep going.
All right, and that T state can be written mathematically down here at the bottom of the slide, and visualized on the blocks here as the vector, the green vector, pointing at the 45 degree between x and y axis. Okay, so this circuit achieves the logical operation on your logical qubit. Now the catch is you have to prepare those magic states, right? So how do you make those magic states? And that is what we call the magic state distillation. So the idea is very simple. One way to make magic states is that maybe we can find it's by code switching in short, but what that means is you can probably find a code, a special code other than surface code that allows for transversal T gate, right? Then it's easier to implement. Then what you can do is on top of surface code, you can encode to a high level code that allows for transversal T gate. So encode those logical qubits to that code, apply the transversal T gate to them, and then detect any error. And if you have an error, you start over. If not, great, you keep going, and then you can decode it back to your logical qubit. that achieves a higher, that will give you a higher fidelity magic state because you have the error detection in the middle that helps you filter out the bad ones. So to be more specific, the success probability of this protocol, or in other words, the probability that you keep, you did not detect the error and you keep the magic state, is about 1 minus order of p, where p is the input error probability of your original T magic state, or in other words, the T gate. So the output of this magic state is has improved fidelity because the error probability is smaller than before. Since p is the number between 0 and 1, you raise it to the d's power, it should decrease. And in particular, d is the dimension of the code. And in Javadi-Abhari protocol that we use for our purpose has d equals 2. So it's a protocol that improves magic state fidelity quadratically. Okay? However, sometimes quadratic improvement is not enough. So what do we do in that case? It turns out that we can sort of concatenate multiple rounds of such distillation and get higher order of improvement in terms of fidelity. And the way we do it is that you run through your circuit and then get a set of magic states better than before, but you feed those magic states into the next round of distillation, and then we'll further improve. And to be specific, if you concatenate L level of this distillation, what you will get at the end is a error probability at the order of p to the d to the L. So that's a very good improvement in terms of error probability, fidelity. So that's actually what we call, what commonly called the block code construction of distillations. And sometimes we call this full procedure the distillation factory. And showing here, each black box here is one of the distillation circuit that I showed earlier. And as you can see, I drew 2 rounds of them. Each round consists of multiple modules, and each module hopefully output k number of better magic states by taking in about 3k plus 8 number of input magic states, and that's the I guess the input-output ratio of the Javadi-Abhari distillation protocol. And furthermore, to avoid correlated error, for example, let's say the block, the bottom right block is really erroneous, and it outputs lots of bad magic states. What we don't want to do is to send those states all into one of the blocks next round, because the parity check there might fail and it did not improve any of the magic states. So what we do is to distribute the output from one module to different modules in the next round. Okay, to just distribute them. As you can see, that forms a permutation edges through different rounds. Okay, so that's our block code construction. And as you can see, this can quickly go very complex, this procedure. How complex is it compared to the entire computation? Turns out that in most applications, it dominates the overhead. For example, 98% of the resources you put into the computation is actually just to prepare those magic states. And only about 1.3% of the chance you are doing actual work. So it's actually a great motivation to optimize for the distillation procedure. And that is why we focus primarily on that kind of circuit. Although our circuit is very general, can be applicable to different circuits, we primarily look at the distillation. And I'll hand it over to Adam to talk about the specific method that we came up with.
Cool. All right. Switch sides here.
Yeah.
Okay. Yeah, so basically what we've come up with are, in this context, there are some unique optimization problems. And so we built basically an automated system for taking circuits that you want to try to run on a surface code error-corrected machine, and you want to make them run as quickly as possible and require as few qubits as possible. And so, that's sort of the general context of the methods that we've developed. We did tailor our methods specifically to distillation structures, distillation circuits, and there are specific properties that we're going to highlight that guided that development. But basically, at a high level, one of the major takeaways from this work was that we tried first to do sort of global distillation circuit optimization. So we wanted to look at these rounds occur separated in time, and we wanted to try to just optimize the entire circuit block at the global scope. And it turned out that actually underperformed a method where instead of doing that, you actually cut sort of nicely shaped subcircuits out of the general circuit and optimize those independently. So that was the building block of our techniques that I'll go into some detail here and highlight. So just again, what we're going to try to do here is instead of optimizing this entire procedure, we're just going to focus on one round at a time first. The reason for doing that, this actually reiterates the point before, each one of these blocks is, again, performing this distillation procedure. So this is code that runs in the scaffold programming language, and we implemented the Braids distillation protocol, which, again, does the sort of encoding to a different stabilizer code, transversal gates, decoding, and each one of these modules here, in each round, is running that code. So to map these modules, we noticed a few things, starting from circuit interaction graphs. So we just looked at, for this, what I'm going to show here is a 2-level factory. So there's 2 rounds, and it's going to spit out a total of 4 higher fidelity magic states. They're 4th order error reduced at the end. And so this is an interaction graph describing this entire circuit. So each node in here corresponds to a logical qubit in the circuit, and each edge corresponds to a 2-qubit interaction. What we did first was notice that there are these nice regular substructures in here, which you might guess correspond to the first round modules that are all disjoint, and then they all sort of join up here in the center. So the first approach that we used is sort of a pretty common one for doing sort of graph embedding problems. Recursive graph partitioning takes some interaction graph and takes some target graph and finds a min cut in your interaction graph and takes a cut of your embedded graph and then maps those partitions one-to-one, and you recurse until you've mapped every entity in your interaction graph into your target graph. So it turns out if you use that procedure on a global structure for this entire distillation circuit, you get some pretty good results. But it turns out that structure or that optimization procedure is really good at mapping planar graphs. And it did turn out that if you extract these submodules here, they are regular planar graphs. So we used that to build up mappings based on each individual module, individually optimized with graph partitioning. We wanted this to be an automated process where we can take an arbitrary circuit, we can discover these types of substructures. So we just used sort of traditional community detection algorithms to do that. This is taking a random walk through your circuit interaction graph and defining communities based on certain width of or certain length of those random walks. And this automatically did detect the sort of hierarchical structure of distillation circuits. So at this sort of scope, what we then did was we took those clusters and we mapped them to your service code sort of grid. So this is a picture where each individual vertex corresponds to a logical qubit, and each color it corresponds to the corresponding cluster from the clustering of the interaction graph. And the edges are drawn, and you'll notice that there's a lot of there are a lot of edges drawn from the entire grid up into the top left of that, the top left quadrant there. And that represents, what's occurring here is that the center two modules of the interaction graph are the next round modules. So they're sort of the first round modules, which are these satellites, and then there's the second round modules that accept as input all the states from the previous round. So those we arbitrarily map with this image into the top left quadrant, and so there's a very large, sort of permutation matrix problem. And all of those edges are scheduled in parallel as well. So there's a very large congestion problem that actually does account for roughly 60 to 70% of the latency of these distillation circuits altogether. If you remove that, you end up with these nice disjoint substructures that are all nearly optimally mapped by graph partitioning techniques. So just sort of showing this at a different angle, if we wanted to pull out the second round modules, right, this sort of tries to clarify what we're trying to do. This is the same grid but separated in time, and we want to take these second round modules and place them in such a way that these permutation edges are minimally congested as possible. And so we develop a set of basically like force-directed annealing heuristics that we're going to use to smooth out this congestion all throughout the machine. First thing we did was we just tried to shorten edges. This is sort of, actually, some of these were inspired by like nice graph drawing techniques, how to draw nice graphs. And so here, every vertex that's connected to another one via an edge has an attractive force placed on it to one another. And then as you let those vertices anneal throughout your surface code grid, the drags connected vertices together and you end up with these clusters. We combine that with a heuristic that spaces out disjoint edges by placing repulsive forces on the midpoints of each one of those edges to sort of spread out these edges uniformly around the machine. And lastly, we did this pretty cool sort of simulation of magnetic dipole moments. And we pretended that each edge represented a magnetic dipole, and you can assign some magnetic charge, a north and south pole, to each edge endpoint of that edge. And then, similar charges repulse each other, and opposing charges attract each other. And so this actually, I'll just show that again. It's pretty nice because it will take edges that are currently crossed on your machine and will attempt to sort of rotate them out of crossings. So those were our sort of heuristics that we used, and we wanted to quantify how well those things actually capture what we're trying to do, which is optimize the latency of these circuits. So each one of these heuristics induces a metric, and each one of those metrics, what we did to study how well they mapped to optimization was to take our distillation circuits, we randomized the qubit mappings on these surfaces, and then we calculated and plotted the performance of the circuits and circuit latency against the value of the metric at any particular time. And so sort of naturally what you see is that, for vertex attraction, the average edge length is the induced metric, and as that edge length decreases, you show, some correlation with increasing performance, decreasing circuit latency. And again, with edge repulsion, you do also see that it's negatively correlated. So as edge spacing increases, you get better performance or lower circuit latency. The edge crossings metric induced by the dipole moment stuff. So that was, this number here, this metric is basically looking at if you draw all the edges, in like a geodesic path on your grid. So you're not actually following rectilinear paths. If you draw those directly as they are, that crossing number is what we're counting here. And, it's pretty highly indicative, more tightly correlated with circuit latency than the other two metrics. But edge crossing numbers are pretty hard to calculate. It's pretty hard to directly minimize that. But, it is actually it doesn't more accurately capture what we're trying to optimize for.
I do want to add on top of that the circuit latency was calculated by our braid simulator that we built from scratch. The simulator essentially schedules all the braids, and it's cycle precise up to the surface code cycle, and it can avoid congestion, do the routing, and then we compute the circuit latency in terms of the surface code cycle.
Okay, so those were the tools we developed, and we want to use those to sort of optimize this sort of permutation step between rounds primarily, because that is where the source of most of our latency is coming from in these circuits. We can diagrammatically sort of walk through what's going on as you permute output states from previous rounds to input states in the next round. This diagram would show, for example, you have 4 modules that are happening at, I guess, round 1 in this example. And they're all modules that create 2 magic states as output. If you wanted to feed those output states into input states of a higher level round or a next level round that is mapped, this is actually physical space here, so it's mapped below spatially. You need to make sure that, again, to avoid correlated error, you only send a single one of those output states, one from each of the previous round modules into a single round of next, single module of the next round, and then you do that for every input state that you need. And if you do that arbitrarily, these networks can get pretty congested. And again, these are all edges that are representing interactions that are scheduled at the same time. So there's a lot of actual real congestion here. What we did the first optimization we did was just to reassign those ports in a smarter way. You can just sort of greedily walk around all the input state ports and look for your nearest output state port from the previous round, and you can sort of reshuffle your assignments in such a way that it cleans up the assignment at this first level. That was our sort of first approach, at just starting from a sort of a clean slate. But then what we wanted to do was try to make this, try to introduce our metrics and our heuristics. So what we did was we took each one of those paths from output state of the previous round to input state of the next round, and we introduced an intermediate hop along the way. We first tried true to form Valiant style randomized intermediate hop destination, and that does actually increase the performance a little bit. Starting from those locations, what we can do then is we anneal all of these red dots indicate the midpoint. We can anneal those endpoints with respect to each other, following trying to find a force equilibrium formed by the sort of potential energy landscape of the 3 heuristics that we used. And this does pretty well. So again, this is sort of the bulk of the congestion of the bulk of the latency induced in these entire circuits. And following this type of technique, we actually can reduce congestion in these steps by about 25%-ish. So with all that, how did we do? How does this sort of stack up all together? The first thing we wanted to look at was to make sure that we did single level rounds, single level factories, or just a single distillation circuit pretty well. And these things, so we're comparing against a baseline called linear mapping, which people have spent a lot of time sort of trying to hand optimize these things and place qubits exactly where they need to be, because it's just a simple small circuit, so they can do that. And we do find that our techniques sort of recover those numbers at the single level factory scope. When you go to multiple levels, our techniques start to show some benefit on top of, sort of the extended hand mapping. At our best, we can reduce circuit overhead by a factor of 5.6, and that's coming from, a lot of it's coming from latency, as you can see here. And so that's sort of the amalgamation of all these techniques into an automated set of tools that really can just take that distillation circuit and perform all these optimizations one by one. Yeah, so with that, Yongshan will wrap it back up.
All right. So in conclusion, the few characteristics of the circuit and also error correction that we studied was basically braiding that can cause congestion, and we want to come up with techniques that minimize those type of congestion. And the particular circuit that we look at is this magic state distillation, because we have shown that it dominates the overhead. So first thing we studied was that we want to find the correlation between circuit latency being simulated, the real time you need to execute a circuit, with our edge crossing number, for example, and we find out that they are really highly correlated, and it inspired us to come up with a set of heuristics that also motivated from force-directed annealing approaches to reduce the latency by intelligently map the source and destination qubits. All right, and we compare those results with the best known 10th optimized mapping, and as Adam showed just one slide earlier, our improvement is very significant, and the improvement comes from a series of techniques that we use and we call hierarchical stitching, because we optimize the mapping by looking at individual rounds separately, and also optimize the permutation between each round. And that's why our optimization technique performs really well on circuit that has hierarchical structure. And as Adam mentioned very early on, our tool can automate the detection of those structures and apply to larger set of circuit, not only just magic state distillation circuit. Okay, so as promised very early on, we have a number of future work immediately extended from this line of work. And for example, another way of achieving long-distance interaction or even manipulate qubits on surface code, other than braiding, is called lattice surgery. And it is the mapping problem in that scheme is even more intricate and more complicated, and our procedure has the promise to even impact this overhead even on a larger scale. So that's one thing that we'll be looking at. And to study the error propagation and also how fast we can keep up with the whole error correction procedure, we also want to look at we're also looking at the hardware accelerator for the decoding procedure of the surface code error correction scheme on superconducting technology, for example. And last but not least, we also want to look at how noise affects the scheme and how our mapping affects either perform better or worse under different physical noise with surface code error correction. Okay, so that concludes our talk today. Thank you very much for joining us, and thank you everyone who called in remotely. Hope you guys heard us clearly. And thanks again. That will be all for our talk. Yeah, we will take any questions from remote callers too.
So you talked about the start. Has your talk started yet?
Sorry?
Nothing. So
no, I didn't catch that.
I have a question. I think I maybe just missed it. There I am. Oh, right here. So the correlated errors. Can you say a little bit more about? So it seems like the correlated errors are the reason why the qubits have to travel so far, right? Because you want the first round and second round blocks to just be
independent,
uncorrelated, which ones they have. So then, yes. Why? Can you say more about the nature of the error correlation that you're afraid of? And is it possible that that assumption is being too strict, and you might find some savings by relaxing it?
Okay. Yeah. The question was what is can we explain the correlated error that we mentioned earlier between different rounds in more detail, and what would be so if we relax that constraint, is there any benefit or loss? Okay, so as I explained it earlier, the correlated error, for example, come from if you have an erroneous block on the first round, you don't want that error on both qubits, for example, the two alpha qubits, to travel to the same module, which means that the module in the next round, where it performs the parity checks, might fail to detect the error. By parity check, I mean, in some sense, higher level abstraction is that we compare the two qubits, and if they're different, one must be wrong. But if they are both wrong, we missed it. So that's in order to make the different rounds independent, we want to send those alpha qubit to different locations to perform parity checks. Even if we relax the correlated error constraint, we still need to send those alpha qubits to the next iteration. But we imagine there will be less crossings because of the permutation pattern will probably be easier to map, since we can just send closer qubits to the next round module to be closer. However, I don't have number of how much correlated error affects the overall error reduction yet, but I think I guess we can definitely study how relaxing it affects the mapping complexity. Did that answer your question?
Yeah, I see. So it's sort of like I get it.
Okay. Yes, Chris?
It's a really theorist question, but between the outputs of one round and the inputs of the next round, it's like a complete bipartite graph, and the crossing number of that graph is like super well studied, and like.
All right. Yeah. So the question was. Could caller mute? Picking up echoes. Thank you. So the question was that since the permutation step we talked about, that sending qubits from the output ports to the input port of the next round is like a bipartite graph, and the crossing number of a bipartite graph is well studied, like how to minimize crossings also. Have we looked at this? So maybe Adam, you want to answer?
So we didn't look at it from that perspective. Let me go with no there. Sure, I'll come over here. No, so we didn't look at it from that perspective. But no, I mean, I think that would definitely be a source of new ideas for how to do this. I think, one of the things that in our sort of example was that we, showed that the second round could be mapped spatially away from the first round, and you would actually have to send these things through space to get to their new destinations. So that second set of destination bits would be separated spatially. But one of the things we did sort of try to look at was, what if you didn't actually move those? If you just reuse the same qubits from the original round, how much does that save you? And yeah, that's ongoing, but it does help.
And to add on that, since the edge crossing number, where you have a direct path from the two nodes, are not exactly the braid path, because what we are using for the braiding is the XY routing, so it's essentially a right angle path. So even though we have studied the statistical correlation between the direct path and the XY routing that we simulated, there is some difference, and we are definitely interested in the optimization procedure for minimizing edge crossings and how that translates to the crossings of our XY routing braids. Yes.
So maybe a related question is, you studied different sort of planar graph drawing or embedding programs, right? Like you used some planar drawing algorithms, right?
Yeah.
Which in some sense would implicitly have some of this crossing number.
Yeah.
I don't know if they incorporate, what an optimal crossing number would be for a bipartite graph. Do you know?
So,
You use
yeah,
some
I mean,
established algorithms, right?
Right. Those heuristics were inspired by those
Yeah.
graph drawing algorithms. And that's where we got, that's where we developed sort of these approaches based on edge crossing numbers, but specifically tailoring it to like algorithms that were developed for crossing numbers of bipartite graphs could be another source of those types of heuristics. Yeah.
One more comment there. Because actually, I recall that the feedback for the graph, the optimal drawing is like pretty simple from two problems.
Okay.
We're checking though.
Yeah.
Yeah, question?
I had a question about the magnetic dipole reduction repulsion technique. Do you mind flipping back to that slide?
So the question was related to the magnet dipole moment technique.
Yeah. So it seems like if, let's say, on the right hand of the magnetic dipole, if you switch the charges on the yellow from plus and minus to minus and plus, then you'd not end up with the crossing. So did you guys like experiment with assignment of charges, or
Right.
like?
So yes, we did. And the assignment was done by like a 3D way of two color, the whole graph.
I want to repeat that for them.
Oh, the question was on this diagram showing on the right-hand side, under magnet dipole technique, if we swap the charge, the positive and negative charge of the yellow node, it will not actually reduce the crossing. So, and the question was, did we try different assignments? And the answer would be yes, because we start out this assignment by doing two coloring of the graph, and it will use force direct annealing and cool down to some equilibrium. Some crossing, as you mentioned, might still exist, but then we also break it up to randomize this process and then do it iteratively to try to go to, I guess, global minimum as close as possible.
Yeah, there are multiple rounds of sort of random selection of those.
A reassignment, if you will, in two coloring.
I think I saw that Yiping raised a hand on the meeting.
Hi, thank you. Can you hear me? This is Margaret.
Oh, hey, Margaret. Yep, we can hear you.
Great. So my question is actually in the chat box, if you can see that. Basically, the way you presented the talk, it sounds like there's sort of a sequence of a bag of tricks of different optimizations. One of which that you mentioned very quickly was about Valiant style routing, which, as far as I know, is sort of routing to an intermediate point.
Yes.
Is that what you mean by it?
Yes.
Yes.
And so then my question is, so much of the pictures that you're showing show a huge amount of structure and order to the graphs. And so I guess I'm wondering whether Valiant style routing to an intermediate point reduces that structure rather than harnessing it.
Well, so the reason that we chose to do that was because we wanted a technique that would scale up first and foremost, I think. For very large distillation factories, as you would need in large applications, it was difficult to come up with a very, deterministic constructive approach for finding these routes. And it actually, so it does look and induce some randomization to the paths that are actually taken. But it's, that was sort of a guide to using the heuristics in the first place as well.
Yeah.
So it both, shows off the strength of the heuristics and, it helps the system scale up pretty quickly.
Yeah, I want to mention that our intermediate hop did not destroy the structure of the circuit because we only introduced intermediate hops for the permutation step between the rounds. And as you can see, it's just interaction between pairs of qubits that all want to happen at the same time. However, we don't apply those intermediate hops for circuit within the rounds because that can already be very cleanly mapped using either our force-directed annealing procedure or graph partitioning, since they are mostly planar graphs. So I guess the short answer to your question was our intermediate hops randomization only introduces the randomness into the permutation step alone and did not destroy the structure of our circuit.
All right, so, okay, one last question. We got to move on to the private exam part of this, but.
So why do you have to embed onto a grid in the first place?
So the surface code error correction protocol works really well on grids. Oh, right. So the question was, why do we have to embed on a grid in the first place? And that's one of the nice things about surface code is that it relies on local interactions that can be performed on a rectilinear grid. And, you know, we're really good at printing those types of circuits in general, and so it leverages a lot of that, you know, manufacturing power.
All right. Thank you, everyone, for coming. Grab some pizza on the way out if you like. There's plenty left.
No.
So, Margaret, please stay on. And thanks all the other EPiC people for coming. And we'll have a recording of this, and if people missed it. And let us know if you have any feedback. Thanks a lot.
Thank you.
So, do you want to maybe move this over to the table so we can talk a little bit?
Sure.
Oh, send the slides to Margaret. Do you guys stop the recording?
It still says it's being recorded.
That little red dot? Oh, you don't know how to stop it?
Yeah.
How did you? But he doesn't know how to stop recording.
Maybe it's on the screen that's sharing.
My
It
screen
says
is
you're
sharing.
sharing, yeah, so go up to the top of it.
Okay.